All right, problem of the day. Number 4. So problems of the day, I guess as it were. This first one was an E2 reaction. So E2 reaction means you're going to make a pi bond. You have a reactive charge base, usually fairly bulky as well. And you want to make sure you get the beta hydrogens that are anti-periplanar. So here you're presented with two. Here's the alkyl halide. It's a secondary alkyl halide. And you're presented with two things, two hydrogens. And the question is, which one should you go for? And I know it's these two beta hydrogens, not these three, because of the product, more substituted product. But there's a wedged H and there's a hatched H. The bromine's wedged, so that means I need to take the hatched H because that's the one that's anti-periplanar to it. And that gets us to our E2 product. And you can see, how do I know it was trans? Because on the product, the two H's are on opposite sides, and they're on opposite sides here. So the methyls would be 2. So that's an E2 reaction. That anti-periplanar, 3 arrows, 1 step. Got to get the H that's on the opposite side of the bromine, the beta hydrogen opposite of the bromine. All right, the second problem of the day was an oxymercuation demercuration. So just remembering what we know about this reaction. For the regio selectivity, we get a Markovnikov product. So that means the solvent, whatever the solvent is, adds the more substituted carbon of the alkene. Right, so in this case, our solvent's water. So we're going to make an alcohol, but it could be any polar protic solvent. So we got to be careful with that. So it's going to add to the more substituted carbon of the alkene. We end up getting the two things we add, the solvent and the H. Should be trans. That doesn't matter here. Can't tell, but that's the case. That's the stereo specificity. The last step, this NaBH4 replaces the Hg, the mercury, with an H. Nothing else changes. We also know there's no carbocations in this as well. And we also know the first step has 2 or 3 arrows. So I'll draw with showing it with the 3 arrows. So it's very similar to the thing that happens with the halogenation when it's with Br2 or Cl2. We get that first step, pi bond reacts, get that syn addition. There's the mercury plus OAC still on there. I can draw in some wedges and hatches. And it's always good to draw in your H's on the alkene to start. No carbocation. The solvent's going to react now. In this case, the solvent's water. So it's going to react with the more substituted carbon. And that SN2, so the SN2 takes place with the solvent, wherever the solvent is. SN2-like. As that adds in, you break that mercury carbon bond, right? And so you get that, this is that trans product, you get that trans addition. All right, so our solvent has added in. It doesn't matter, in this case it's water, just any polar protic solvent will work. Ron's has an OH, NH, SH, or pH. So the water is added in. The last step before we go to step 2 is actually just a deprotonation. All right, so just a deprot. And you could have another water come and do this, or you could literally just have the H fall off as H+. That's fine. And that'll get you to the alcohol version of this. And then the last step, the step 2, is that NaBH4. That'll get you to the final product. The other version of this, it doesn't really matter. And then the question I had, did you make an asymmetric center? So obviously the place we added things, right? We added H here, so there's 3 H's there. So that's not an asymmetric center. But at this carbon, we added an OH, and there's an H, a tert butyl, and then a methyl. So this is an asymmetric center. So yes, we did make an asymmetric center here. So we'd say plus an enantiomer on the product here. Yeah, just a full reminder, what the NaBH4 does, you don't even know the mechanism, it takes an Hg and turns it into an H. Don't move it at all, just literally Whatever was an Hg, put it as an H instead. You're done. It's kind of like the hydroboration oxidation. Whatever, when you have the boron there, you just replace the B with an OH.